Here is a barrier with two narrow slits, and behind it, a detector. We send a particle in. It eventually appears as a single dot somewhere on the detector. The natural question is, which slit did it pass through? In the next 8 minutes, you will see that this question has no answer. And the failure of that question reveals the deepest truth in physics. Let us start with something simple. Bullets. Imagine a machine gun firing at the barrier. Most bullets are blocked. A few pass through slit 1, a few through slit 2. Each bullet definitely goes through one slit or the other. Mathematically, the probability of landing at position y on the screen is just the sum, p of y equals p1 of y, plus p2 of y. Two Gaussian clumps, one behind each slit. Probabilities add. Common sense. Now switch to classical waves. A water wave or a light wave hits the barrier. By Huygens's principle, each slit becomes a fresh source of circular waves. The two circular waves spread, overlap, and interfere. Pick any point P on the screen. Two rays connect to it, one from each slit. Their lengths differ by an amount we call the path difference, capital delta. Here is the geometry. Drop a perpendicular from the upper slit onto the lower slit ray. You get a right triangle. The hypotenuse is d, the slit separation. The angle at the slits, between the baseline and the rays, is theta. So the small leg, the path difference, is delta equals d sine theta. Constructive interference happens when delta is a whole number of wavelengths. D sine theta equals m lambda. That gives a bright fringe. Destructive interference happens when delta is half a wavelength off. D sine theta equals m plus a half, times lambda. That gives a dark fringe. For small angles, sine theta is approximately theta, which is approximately y over L, where y is the position on the screen and L is the distance from slits to screen. Putting it together, the spacing between consecutive bright fringes is delta y equals lambda times L over d. A simple, exact prediction. Stripes of bright and dark, evenly spaced. So far so good. Bullets, two clumps. Waves, fringes. Two completely different signatures. Now we do the experiment that broke physics. We replace the bullets with electrons. Solid particles, each carrying mass, charge, momentum. They should behave like bullets. But Louis de Broglie showed in 1924 that every particle has an associated wavelength, lambda equals h over p, Planck's constant divided by momentum. So between source and detector, the electron does not travel as a tiny ball. It propagates as a wave function, psi of x and t. The wave hits both slits at once. From each slit, a fresh wavelet emerges. We label them psi1 and psi2. The total wave function on the right side of the barrier is the superposition. Psi equals 1 over root 2, times the sum of psi1 and psi2. The Born rule then gives the probability density on the screen, the modulus of psi squared. And that probability density shows fringes. Identical, mathematically, to the wave case. Single particles, producing a wave pattern. Let us slow this down. We dim the source so only one electron is in the apparatus at a time. We see one dot on the screen. Then another. Each individually random. There is no electron flying through space between source and detector. There is only the wave function, spreading. The particle does not exist as a point until it strikes the detector. After thousands of these single events, the dots are not scattered randomly. They are not in two clumps. They build up, dot by dot, into the same fringe pattern. Each lonely electron interferes with itself. Now let us ask the question that started everything. Which slit did it really go through? Suppose we put a detector right at slit 1. A small device that registers if an electron passes by. We try to catch it in the act. The instant we observe the electron at the slits, the wave function collapses. Only one of psi1 or psi2 survives, because the electron has been measured to be at one specific slit. The superposition is destroyed. When we now run the experiment, the screen no longer shows fringes. It shows two clumps. The electron pattern reverts to bullet behavior the moment we extract which path information. Mathematically, the modulus of psi squared no longer contains the cross term. It is just the modulus of psi1 squared, plus the modulus of psi2 squared. The interference term is gone, because the wave function has collapsed to a definite slit. This is not a technological limitation. It is fundamental. Observation changes what is observed. So why do fringes appear at all? Because, when both slits are open and unobserved, the amplitudes add before we square them. Take the wave from each slit as a complex plane wave. Psi1 equals a times e to the I k r1, and psi2 equals a times e to the I k r2, where r1 and r2 are the path lengths. Now compute the modulus of the sum, squared. You get three terms. The modulus of psi1 squared, plus the modulus of psi2 squared, plus an extra cross term, 2 times the real part of psi1 star times psi2. That cross term is the interference. It carries the cosine of k times r1 minus r2. Substituting our path difference geometry, the closed form is, the modulus of psi squared is proportional to cosine squared, of pi dy, divided by lambda L. The fringe pattern, exact, derived from first principles. The lesson of the double-slit experiment is one sentence long. Add amplitudes, not probabilities. This single fact, that quantum mechanics combines complex amplitudes and only squares them at the end, is the origin of every quantum surprise. Let us bring it together. 1. Bullets give two clumps, where probabilities simply add. 2. Classical waves give fringes, governed by d sine theta equals m lambda, and fringe spacing lambda L over d. 3. Electrons, fired one at a time, also give fringes. They are waves. 4. The total wave function from two slits is the normalized sum, psi equals 1 over root 2 times psi1 plus psi2. 5. The probability density contains the interference term, 2 times the real part of psi1 star psi2, which is responsible for the fringes. 6. If we measure which path the electron took, the wave function collapses, the interference term vanishes, and the pattern returns to two clumps. In the next episode, we will give this principle its sharpest, most quantitative form. The Heisenberg uncertainty principle. We will see that there is a fundamental limit to how precisely we can know two complementary quantities at once, like position and momentum, and that this limit is not technological but written into the structure of nature.